Do you want the presenter's view or not?
No.
No, right? Yes. Yeah, there are not many people there. So, it's busy. Oh, good. Okay, good morning everyone. So today, as I mentioned before, that we have a industrial lecture, the first one. So Donald is from PowerLink Queensland, and then Donald has quite a vast experience on this power system protection and then transformer protection. Donald, I think, is a senior engineer there. Principal engineer, right?
Changed the title.
Yeah. So, sort of principal engineer is above the senior engineer.
True.
And Donald has been there in PowerLink for last probably 38 years. So he has vast experience in this field. So I would like to share your experience with us, and then you can go out of these presentation slides and then discuss other things to give them some sort of a industry experience. That would be good. Okay, thanks a lot. Thanks a lot for being here.
Yeah.
I'll over to you.
Yep.
Just take my stuff.
Thank you for that introduction. Yeah, actually, PowerLink hasn't been around that long. To be honest, PowerLink started about 94, so getting towards 30 years ago when they split the industry up. So when I started, it was Queensland Electricity Generating Board for about 6 months, and then it became Queensland Electricity Commission. And we had PowerLink, which we are now, and all the generators across Queensland. And we didn't interconnect to New South Wales. So Queensland was just an island. The interconnection come in the late 90s. That's when that got connected to New South Wales. And they split government-wide across Australia. They split up the electricity industry, which was the old government ones. We're still government-owned, but in New South Wales, Transgrid is now private. So some areas have privatised. South Australia is on a 100 or 200-year lease, I forget which one. That happened 20 years ago, so they've still got a long time to go. Anyway, get into this. If you've got any questions, ask as we go along. I don't know how we get that on the Zoom, if there's an area there that questions can come up in a chat or not. So primarily I'm going to talk about transformer protection. I cover a little bit on what's unique in the transmission network from a feeder protection point of view. And then if you've got any other questions or what's happening in the industry or what's happening about. I actually forgot my laser pointer, so I can't point up there to things. So does that show the mouse? Get myself on there. No, it doesn't really. Oh well. So these are the typical types of protection that we have in PowerLink. For transformers, we have, under the National Electricity Rules, there are 2 systems you must have, schemes for protection, both running high speed, both in competition with one another. So it's not a main and backup, which happens in the distribution network. We call it X and Y in PowerLink and across a lot of Australia. Some places around the world call it A and B, some call it main 1, main 2. It's all the same. So here the terminology is X and Y. They're totally separate networks, totally separate CTs, VTs, totally separate circuitry, batteries, relays, everything is separate with them. The trip coils on the breakers are separate. The only thing common is the circuit breaker because of the cost. So we cover that by having duplicate breakers, by having a circuit breaker fail scheme that covers that. So for the transformers, we start off with our X as being a bias diff and a tertiary overcurrent, and the Y is just a bias diff and a tertiary earth fault. Earthing transformers have an overcurrent on the X and another overcurrent, neutral and definite time on the Y. Our cap banks have basically overcurrent and a high impedance or another overcurrent, depending on the voltage level that we've got. We've also got a balance protection, and there's a pole discrepancy on the X and an overvoltage on the Y for the cap banks. They're standard, and what we've found for our network is that it's cheaper for us to have the one type of protection for different voltage levels. Having different protections for different voltage levels means, carrying more spares. Newer design, you've got to think about it. It just keeps it simpler for everybody. We've got one panel and it's the type of protection, feeder, transformer, doesn't matter what voltage levels it's at. So for our feeders, we have a current diff on the X and a distance on the Y. Problem with distance protection is that if you get very short feeders, you can have an issue with the distance discriminating. So we have duplicate current diff on that. The bus zone is usually high impedance, X and Y. And for isolator selectable buses, we have a low impedance scheme. Do you want me to grab that one? I'll grab that one. And shunt reactors, we have negative phase sequence and high impedance. Most of our shunt reactors are on the feeder, so they're also inside the feeder protection as well. Now this is national electricity rules, they're fault clearance times. Powerlink's network operates at 110, 132 and 275 kV and 330. So you can see that the times to clear faults are about 100, 120 milliseconds we've got. So that's quite high speed to detect, clear correctly as well. So you don't want to be tripping spuriously and you haven't got much time. So for that you need communications largely, or unit type of protection. The remote ends are given a little bit of time, that's in relation to feeder protection, to acknowledge that you've got a signal to the other end. Why you need 220 at 132 kV or 220 kV I don't know, but that's just how the rules were written back about 30 years ago. And they've got a breaker fail time in there as well. So this is a typical looking transformer. It's a bit of an old picture. We don't have down on the bottom left corner a hand wheel for manual tap changer anymore. You've got the windings inside there. On the right hand side you've got your cooler, and that can be just a natural convection, or it could be with pumps, pumping it around, or it could be pumps and fans, or natural, like I said at first. So there's those three types of cooling, and that depends on the temperature of the transformer. As you use pumps and fans, they use electricity, so your losses are higher. So if you're not heavily loaded, you don't turn them on at all, your transformer doesn't get too hot. Up on the top right there, you'll see, or not quite top right, the Buchholz relay and an oil temperature, oil gauge level, to see your level there. And that's in the conservator up on the top there. And inside the transformer is also oil and winding temperatures, OTI and WTI, they get abbreviated too. So transformers are highly reliable. We don't have many transformer faults, but they do occur and you do need to protect them. In fact, all plant items under the National Electricity Law need protection. If you don't have protection on the item, you've got to take it out of service. When faults occur, they can be quite damaging, some of them, some not so much. And you must provide the speed. We've got the rules to how fast we've got to clear them. Part of that reasoning is for stability of the network and damage to plant. If a fault hangs on longer, it's more likely to cause more damage and cause you stability issues in the network. The problem also with transformers is that they've got a lot of oil in them, so there's always a fire risk with the transformers. This is one transformer, and that's how it started, and there was one, I remember when I was a young engineer, we put some new transformers down at Tennyson, 3 new transformers down there, and within a year one of them was on fire, burnt up, a brand new one. So that's, nowadays you talk about a bathtub curve as risk. It was a new transformer, it failed, and it failed by burning. I don't believe that is the picture of that, but it might be. So it was a 100 MVA, 110 to 33 kV transformer. This is an old one from an old QEGB that sits in the workshop at PowerLink that we took a photo and put it in here. That's a transformer fault. That's the damage to the windings internal. It's not used for anything but archive purposes, and probably go into a museum one day, that piece. But it's interesting, you can see the forces there that have just shifted the windings internally. So they can be quite strong, the forces. So it doesn't need to be, this was a fault in there, but actually no, it wasn't. It's an external fault. That's just what I was going to say. You can have external faults which put a lot of forces on the transformer, so they've got to be designed for that level. If you go above that fault level externally, so the fault isn't in the transformer itself, it's actually mechanical damage. And that's also another thing with fault current, is that it might not be an electrical fault, it could be a mechanical fault. You've got structures which can only handle, or fittings which can only handle certain fault level, and the higher fault level puts more stress on them, and they fail mechanically, not electrically. So that's what's happened on that one there. Why is that not coming up? All right. That might just be a bit of time with that. Oh, I know what's happened there. I added in a couple of pictures. In the last year we had a transformer that failed up at Cumberella Park, which is sort of on the Darling Downs out there. It was a 300 MVA transformer, but I don't know the reasoning why it failed. It had a bushing fault and threw out porcelain around the area a bit. When we build these transformers, they've got a blast wall between transformers. So you have a fault on one transformer, you don't throw porcelain into the next transformer and damage both your transformers that are there. Also, there's a wall around there to help it stop it going out into the rest of the yard if there were people there, and to contain it in there as well. There's oil containment areas. So there were some pictures of those which showed where everything would be. This didn't leak any oil, but it did blow the top of one of the turrets of the transformer with the porcelain in there. Yeah, and the transformer's 18, 20 years old, something like that. It's not new and it's not old. It's not heavily loaded, but I haven't found out why it failed. I don't know that they know why it failed. But types of transformers can be a phase to ground from winding core or winding to the tank. You can have phase faults between windings. You can have interturn faults, so the one phase has a fault in between the turns. Arcing of contacts is another type of fault. Terminal and bushing faults, often animals. That one at Cumberella Park wasn't an animal. And usually when it's an animal, it's on the low voltage side because there's less distance between the phases on the lower voltages. And they're not uncommon on our 33 kV. I've heard a few over the years where a snake has got in winter, curled around the 33 kV windings to warm up and trip the transformer, and they find a dead snake when they go out there. Clean it out and put the transformer and test it and put the transformer hopefully back into service without damage. Usually it's not damaged, they can put it back in, but we have to sort of monitor it that as well. Partial discharge, which can be moisture getting into the transformer, which is a design problem. I say that doesn't probably happen very much in PowerLink. We've got a couple of smart engineers who've been there for decades We specify our transformers, go to the factory and see each one made, witness all the tests, so they're very rigorous. They're rigorous to the point that we buy a certain manufacturer's transformer from a certain factory. We won't buy that same manufacturer from a different factory. So they may have 5 factories around the world and we'll only buy from 2 of them. So we tell them we don't want that. We're not going to buy yours from those factories, they're excluded. So we go to that level, so that sort of issue is not so much a powering problem, but can be a problem for transformers in generalised comment. External faults, which was the other one we saw there, the picture of, which would cause mechanical damage, and overloads on your transformers. If you overload them too long without tripping them, you can cause damage. Yes?
I was just going to ask, so what was a rough order of likelihood?
No, not really. How would... Oh, that's a difficult question, that one.
Yeah.
Whoops, go back. See. Got to go back another one. I went forward. There. I'd say the most common are your terminal and bushing faults. They're the ones that I've seen the most. External transformer faults, probably not very common because we rate our transformer to a fault current rating and we monitor that. Years ago, that other one was a smaller 66 to 33 or 22 kV transformer, so they may not have monitored as well in a distribution board which had 50 people and only 10, 15 engineers, so they didn't monitor those things as well. So that would be arcing contacts. It's just sometimes you get a bad batch of contacts. I've heard that, and tap change is causing problems. They're arcing as they're moving over. So we have an argument with the manufacturer, we get them replaced, and who pays for the cost? They're what another group look after and arguing. So they're fairly common. We don't tend to get internal faults in the transformers very much, would be what I've heard. Overload, no, we tend to take care of that, watching it as an issue. Wherever we can have an N-2, so that means 2 planned items out of service, and overload a transformer, we put overload protection on there, a thermal protection. So they have a 10-minute rating and we trip them off in about 8 minutes. It just gives the operators a couple of minutes maybe to do something and drop some load off. We had some problems 20 years ago where AEMO wouldn't allow us to take an outage. It was actually NEMCO in those days. Wouldn't allow outages. We want to take a transformer out. We've got 2 transformers sitting there. They say one could trip, the load will drop onto the other one, and we go, yeah, all right. The load at that site peaks at 200 MVA. It's typically 150. This time of the year, it's only 120, and that transformer's got an overload capacity to 120. They still wouldn't allow us the outage. So it's not, they were saying, 200 MVA side, you could put 200 onto that transformer and damage it. You go, no, you won't, but they go, you're not having your outage. So we said, what can we do? And they said, fix it up. So we had a portable overcurrent relay we just stuck in there and said, if you go above 150% of the rating of the transformer for longer than 10 seconds, trip it. So they were happy with that. What they didn't want was, we had an outage of a transformer, we damage another transformer that just has a fault on it, and then we damage another transformer, so we've got 2 transformers which are damaged and just 1 transformer. They can take a year to replace transformers if you don't have a spare. They take a really long time to order and get. Pay a bit extra and you might get it for 9 months, but they're long lead items, transformers to buy. That's probably the big concern, was something like that. So overload's not really an issue for us because if it overloads, we trip. It's basically what we've got on it, and at sites which only have 2 transformers, one of those transformers can take the full load, so we don't have an issue. Yeah, that's how I would put the order. A Buchholz relay is internal. It's part of the transformer that you buy. You've got to have a conservator for it to work. It provides really sensitive protection for serious internal faults. It will also cover you for low-level faults that keep going on that you can't detect. Into the winding fault that's just arcing, causing some gassing that... With transformers, they've got tap changes, so the current varies from top tap to bottom tap. That arcing could be less than that, could be seen externally just like on a different tap. So you can't pick it up with external protection. So some people say it's the best overall protection for internal faults. You get local winding heating, local coil overheating, bad joints, partial discharge, a breakdown in the insulation of the transformer. They're all things that the Buchholz can do. For PowerLink, we reduce the risks as much as we can. We take oil samples. We've got a really good lab, which is probably one of the better ones in Australia, that do the testing of all the oil samples and can tell from that how the age, the insulation, how the transformer's going. So we can know it. You can have transformers which are physically been there longer but look younger than younger transformers, which may have been heavily loaded in their life. So these sort of oil tests give us a condition monitoring of the transformers. When you've got a big network and a lot of transformers, it takes to invest in things like that. Your Buchholz will trip for like leaky joints, tank faults, contraction of the oil under temperature or faults, and major internal faults causing surges in your oil. So there's two floats within the Buchholz relay, an upper float which just alarms, and it's really there detecting gas, low-level faults, so you go and investigate further. Serious faults which causes a big fault internally will send a surge of oil through the transformer, and that will trip the lower float, which will trip the transformer. These are a mechanical device sitting in the transformer that just wires out to the protection relays, which go off, just receive that input and take it out to the circuit breaker, and we start CB fail when that occurs, circuit breaker fail. So I use a lot of acronyms, so if you don't know what one is, yell out, because when you deal with them all the time, you begin a bit blasé. To be honest, the industry has changed a bit, and we've got a lot of some non-technical people in management, and they always tell us, in your reports, don't use acronyms. Spell it out. And we go, that's because you don't know engineering. No, we don't say that. Not to them. So that's what a Buchholz relay looks like internally. Unfortunately, I haven't got my laser pointer, but you can see the bottom one. There's it says to trip circuit. So you've got a mercury switch there. You've got a little floating thing there. If a surge of oil come on the bottom left, it'll knock that plate heavily and tip onto that, make a contact, and out and trip. Whereas the other one is a gassing level one. As the oil level varies, that's then when you get a little trip. So that goes off to an alarm. So one of them we want to trip the transformer, we've got a big fault. Another one, there's something internal that's going on that we need to investigate, send an alarm, and we'll get people out to have a look to see what's going on in the transformer. Another one is a pressure relief device, which is often called a Qualitrol. But a Qualitrol is a brand name. It's just a spring-assisted pressure relief device. So when you get internal faults, there's like that oil surge I mentioned, there's also a lot of gas, there's a lot of internal pressure happening. You want to be able to release that. You don't want to rupture your tank, you want to wait for that to get out. So what there is a little device which has got a little hole. When a lot of pressure comes onto it, it opens, lets that pressure out. Oil will probably spill out a bit as well, so there's little things around it to catch it, the oil, and it just prevents tank rupture. It will then go off and trip. There's no alarms with that one because it's a massive internal fault that's sent a lot of pressure through, just to release it. With these, we have the buckles on our X protection and the pressure relief on our Y. So that if some X or Y protection is down for some reason, we've got diversity across the X and the Y protection, rather than putting all our eggs in the one basket. And relay contacts, connected to trip the transformer. That's just what they look like. They're mounted on the side of the transformer, and the transformer manufacturer puts them on the transformers. There's winding and oil temperature that we have, and there's a HV, LV and TV tertiary winding and oil temperatures. So we have 4 contacts on them. The first is sort of to start the pumps, start and stop the fans, and then we get into temperature alarms, which sort of said, the transformer's getting a bit hot, the fans are all on, you're still heating up. Mr. Operator, you need to take some load off somewhere because we're getting too hot. You need to do something. If it gets too hot again, we then put it into we trip the transformer. And the way we do it in PowerLink is we don't trip the transformer like a protection trip, which is trip the HV and LV breaker. We know that temperature is an overload condition. So what we do is just trip the low voltage circuit breaker to drop the load off. That keeps the transformer energised so the operators know there's nothing wrong with the transformer, it's just hot. So you need to take some other action to drop the load off, but you can put the transformer back in service whenever you want to. You don't need to send people to field, or you make a choice on that. So a long time ago we used to trip both the HV and LV, we didn't distinguish, then we started to think about it and go, this isn't a fault on the transformer that we need to de-energise the transformer, we need to deload the transformer. For us, when we energise a transformer, it's always from the high voltage breaker to the low voltage breaker, so we trip the low voltage breaker, is what we do in that case. There's winding and temperature, or oil temperatures in there. Winding you'll see is higher, and that's because that's where the current's going through. That heats up quicker, but it takes time for it to get through the oil to heat up the oil. The oil is going out into the vents and fans, so they're cooling it down, coming back in. That's why you see the difference between the oil and the winding temperature as far as the temperature. They're sort of guidelines. Different utilities will do that at different temperatures. I don't even know our standard temperatures. We just got a standard temperature where we set all of those at, and that's in these devices, and we never change them, to be honest. It's been working for a long time. Fuses are typically used in small transformers. We use them in our local supply transformers. A typical substation for PowerLink has our transformers, a delta tertiary with a low rating, and we take off the local supply for the AC for the substation off those delta tertiaries. That's 70 or 80% of our substations are like that. For lower voltage distribution, Energex, Ergon, Energy Queensland, they're called now, mining sites, big factories, things like that, where they've got these smaller transformers, fuses would be all that they need, and they typically rate. Your fuse needs to be rated over the emergency overload, and that limits their sensitivity. For ours, it's not really a problem. We've got a high fault level, a low rating transformer, so the sensitivity is not an issue to faults. What was that last comment I had in there? Is that one? You need to coordinate with downstream protection. So utilities need to be looking that their fuses grade over top of one another. If you've got transformers and then another transformer beyond that, or another feeder beyond that, you've got to grade all your lines of protection. For us, it's not an issue with a local supply. We come at 11 kV off the smaller transformers, 19.1 off the bigger transformers, down to 415 and around in the substation. So there is no grading downstream for us. Common ones are high rupturing fuse, a HRC. And they're generally used for ground level pad mounted transformers. You can have the expulsion dropout fuses for pole mounted transformers. Whoops. Next, as your transformers start to get a bit bigger, you can use an overcurrent and earth fault. That's what we used to use 25 years, 30 years ago on these smaller transformers. As I said earlier, we've got bias diff and we use that one panel of bias diff. Doesn't matter whether it's a 500 MVA transformer or a 20 MVA transformer. It's just quicker for us to go. That's what we've got. Put it in there. This is the standard design. We save a lot of time on that. There's not much difference in the cost of relays now if you were to go just to an overcurrent relay as opposed to the bias diff relay that we use. And when we buy a lot of them, we get a good price for them. So, yeah. But years ago, the electromechanical, there was a bit of difference. There's also a difference in the speed back then. You wanted higher speed, you paid more. Nowadays, that's all electronics. There is no difference. For 10 MVA, they used to be the main protection, and you can use them in up to 20 VA. They can also be used for backup, for higher voltage, higher rated transformers. For us, we sometimes use them as a backup, but we've got the one IED. The modern relays, you can do many things internally in them. So sometimes if we need to back up, not so much for us, but someone else asks us to back up their network, especially Ergon at 66 kV. A lot of their sites have a single bus zone protection. In our transformers, we have an overcurrent relay graded over top of their bus zone protection to trip if their bus zone fails. Bus zones are not very common. Bus zone relay failing is not very common. So it can be, and it's a lower voltage, so it can be a bit slow and just an overcurrent is a backup. In that case, it is a backup, but for our network, it's X and Y. They're racing one another. There's not a backup style of protection. Common up to 66 kV and those ones. There's two ways, or a number of ways you can use it. The overcurrent can be an instantaneous, or you can have it time delayed. You can discriminate on current, time, or very common is a current and time, which is your inverse definite minimum time, IDMT. And the most common type of IDMT is a standard inverse, but there's many different curves. British, IEC and ANSI, I think, is the other one, the American one. So look at the relay manufacturers, they say the overcurrent element inside their relay can do about 15 different curves. Still the most common is a standard inverse. An overcurrent only sees phase currents, so that limits its sensitivity. So you've got to grade it over top of load to be able to do that. And it may need to be grounded with downstream protection as well if you've got protection downstream. That IDMT curve is get higher current, you go quicker. It's basically what it means. An inverse of that. Higher current means slower time, quicker time. They're just the formulas for those three that I've just mentioned there, which are common. The common one like being the standard inverse there. You go into a relay manufacturer's manual and you'll see many different curves in there. That actually comes from a book called Prague, which is a little bit old now, the Protection Relay Application Guide. When I was doing my engineering degree a long time ago, it was a compulsory book that we had to buy. It's now called, I think, Network Automation Guide. I forget exactly, I should look that up better knowing it. And it's a free book on the internet now. It was first done by Westinghouse in England, then they become GEC, then GE, then AB, then Arriva and Alstom, so they're now Schneider, I believe. But they produced that book and published it free on the internet. It's a really good protection book for people. If you're wanting to look at protection, grab that and it gives you a really good overview of everything. Instantaneous overcurrents are actually quite good. They can detect faults on the HV side really good. What you've got in your transformer is a lump of impedance. The fault level on one side might be 10,000 amps for the HV side, the 132 kV side. A fault on the low voltage side might only be 2,000 amps on the HV side, because it's 5,000 or 6,000 on the low voltage side, but as seen from the HV side, it's only 2,000 amps. So you can discriminate your HV terminal faults to your LV faults just on current, and that's where you can set it instantaneously. If that was the case, you set it to 8,000 amps primary and you trip instantaneously. You're not going to trip for low voltage faults because they're a lower current. That's then when you've got to start using your IDMT and grading over top of low voltage current, low voltage protection. But on the HV side, you're using current as the discrimination between the HV, using current to grade over top of that. Earth faults are either a neutral or a residual sum of the three phases, depending on where your CT is located. They only see earth faults, so you can set them very sensitive then. And yeah, they can be set well below load, very sensitive, same sort of comments. The other thing you need to do is, when you do need to grade, how much do you use? This again comes from Prague. You need to allow for CT errors, relay errors, relays operating slower or quicker, breakers operating slower or quicker, and a safety margin. This is what they say should typically, for different types of relays, be used. Practically speaking, everyone still uses that 400 milliseconds. So the 0.4 of a second is the sort of grading margin. It's been used for 40 or 50 years. It's good, it's safe. We don't trip spuriously on that. Why change? That's the sort of comment. You make it shorter and you're tripping correctly, you drop load off and people ask you, why did you do that? When there is no network concern, why do it? That's sort of the comment. So typically we still use the 400 milliseconds, and that just is a good margin that is just proven. It's good, safe, works well. Differential protection, there's two main types and they operate on different principles. Bias diff is based on a balance of ampere turns. So that's what we typically use on our transformers. And the high impedance, which is based on Kirchhoff's current laws, it's something I used to use when I first started working in protection, but is now gone out. There's advantages of both of them and disadvantages of both of them, to be honest. High impedance is sensitive, they're fast. You have one scheme for each galvanically connected set of windings. So if you've got an auto transformer like where a lot of ours are, you have one lot of protection around the whole transformer because you've got one winding. If you've got an HV winding and an LV winding, you need two lots of bias differential, high impedance differential. You may need a metrocell because the voltages can get real high, so it's just really a voltage dependent resistor. Problem with them is the CTs need to all have the same ratio. You can't have a different ratio on your CTs. They're not well suited to delta windings because it's a complex arrangement that you need to do to set them up to have the balanced currents. And because they're so sensitive, you may actually need a shunt resistor to destabilise them. So there have been times where we've gone, that actually only needs a few amps of unbalance. We'd need to put a resistor in there to desensitise it. They operate for faults to windings or earth, to other windings or earth. So this is an example here. You've got current along the top. You've got current in the opposite direction in your CT. You've got a fault on the winding. You're going to get no current down the bottom, we're saying. So current passes through the relay. and that will then trip the circuit breaker. You get an inter-turn fault, they don't operate for those. So you get current in the top like before, but going through the bottom as well. The current circulates in the leads of your CTs all connected together, but not through the relay, so the relay won't operate in that scenario. So they don't work for inter-turn faults. So the same A phase, having a fault between a couple of windings, it won't detect that. If you've got this type of protection, that's going to cause heating and gassing and sorts of things. If it's a high level fault, you'll trip your buckles. If it's a low level one, it'll take a little while to do that, but it eventually will produce enough gas to either alarm or trip it. That's the sort of things you've got going up. Your temperature, if it gets too hot, will trip also. And that sort of thing would be causing the transformer to get hot, even when it's lightly loaded. So it should ring alarms, and then people should say, oh, this looks like that. The way you set these is you assume one of the CTs saturates for an external fault. You work out the voltage across that CT then, CT's current transformer. You select a setting above this, and that means that the scheme will be stable for external faults. That's how simple they are at setting. So here's an example. We've got a 300 MVA transformer. The CTs are 2400, 2000, 1400, 800 to 1. That P 0.1 PX 600 R2 at 400 to 1. That's your magnetising current. The 0.1 PX stands for a protection class. There's two types, PX and P class. PX is just a bit better for transient high-speed performances, and it's what we use in our network. But P class are very common for people connecting to our network, we see. Even high voltage feeders, 132 kV feeders, we see. They build the feeder and put a set of CTs down the other end. They've got two PX for us, for the feeder protection, and P class for their own protection. Nothing wrong with P class, but prefer PX. The 600 tells you the knee point voltage. You don't get that on your P class. R2 is the resistance of the CT. You don't get that on the P class either. 400 to 1, that's the ratio that's at. So at 800 to 1, the knee point voltage is 1200, twice the times of that, and the resistance is twice the times, 4 ohms. So we assume that it's a 13,000 amp fault. You can say select a ratio of 1200 to 1. If you look up at that set of CT, the CT specification, there's not actually a 1200 to 1 written up there. The way you get 1200 to 1 is between 2000 and 800 is 1200. So the actual ratios on that transformer are 400, 800, 1200, actually 400, 800, 400, 600, 800, 1000, 1200, 1400, 2000 and 2400. I've actually dropped that 1400 out of our specification now, but that's how you work. You get a whole lot of ratios there. The reason we do that at PowerLink is because these CTs we buy can go anywhere in the state and can have any ratio on them. If you're designing for a renewable connection or a mine site or a specific factory, you can get your ratio and just have a single ratio CT. That's what you're designing it for. When we order these, when we specify these, we don't know where they're going. It can be anywhere in the state. So we have a big range of that. Also then helps with spares. We can put a spare anywhere in the state. If we wanted a 2000 to 1 ratio but didn't have it in our spare, we've got a whole lot of work to do, and is the CT really suitable? But anyway, getting back to this. So at 1200 to 1, the resistance of the CT is 6 ohms. That's our formula for the relay voltage, is the fault current times the resistance. That's quite simple, V equals IR. We're talking in secondary terms, so we've got to convert the 13,000 amps to secondary amps. So that's why we divide it by 1200. For our standard designs, we say the lead resistance is 2 ohms. It can't be any more than that. So that's what our designers do. Make sure the leads are below 2 ohms. You don't care if it's 1 ohm or half an ohm. It's not over 2 ohms, so we just put 2 ohms in there. So instead of them going out, measuring the wire we've got, the resistance, the length, calculating it all out, we just put in 2 because we know it's below 2. That's just quicker, simpler, actually cheaper because it takes us less time to work that out. But I have seen consultants, they do work for someone, they know their CT here, they've got a 5mm CT cable coming in from the CT that runs 68 metres and they use that resistance of 0.85 ohms. That's technically more correct, but it takes longer to do. If you have a look, work back through this and instead of putting in 2.85, you're going to come out with the same answer. They spend more time to work that out, but and they end up with the same answer. So we get an answer there of 87 volts. So this is one of those high impedance or old electromechanical style relays. So they have the plugs and dials and things like that in them. So the settings range from 25 to 350 in steps of 50. So you haven't got a continuous range. So your options are 25, 75, 125. That's it. So we know it needs to be at least 87. It can't be less than 87. The next available setting is 125. You set the relay. That's it. So if we have an external fault, the CT saturates, will still be stable. If you get an internal fault, you're going to get a whole lot of volts in that internal circuit and your relay is going to trip because it's above 125 volts. So a lot of current, high impedance, it's a high impedance thing. High impedance, high current equals high volts. What you also need to do with these is to check that the neat point voltage is at least 2 times your setting and preferably 5 times. That's another thing for PX class CTs. You've got your neat point voltage there. It is at 1200 to 1, it's the ratio of 1200 to 400, 3 times 600, which is the 400 to 1 neat point voltage, 1800 volts. 1800 divided by 125 is 14.4. We're over 5 times, so we don't need to worry. So we tick that box. The CT is okay. So this is how you'd wire up your CTs. This is a auto transformer. You can see one winding in the middle, and then the tertiary is a delta winding. So what you've got on the left is a proper high impedance scheme. And you'll see going down the page, those solid ones there, that's the neutral, that's the star point, but we're above the star point in each of the phases. So that's why there's 3 of them. That's how you need to connect it. What is another common thing in which we use at times, maybe a bit less nowadays, but recently we've been using quite a lot, is what's called an REF, high impedance scheme, a restricted earth fault. So that neutral CT, that star point CT is below the star point, so it's just in the neutral. So all 3 phases are summed together and the neutral point get together, so it's just looking at earth faults. So what this will do is detect low-level earth faults. And what we've been doing is inside the transformer, in the turrets, we get some CTs put in. They're all the same ratio, and in that neutral point, get a CT put in there. And we put a restricted earth fault around in there. So we're detecting low-level internal faults in the transformer. If we get an earth fault external to the transformer, it's going to be a lot of current, and we use our bias differential to pick that up. Bias differential needs to cater for CT errors, tapping changes, a whole range of things like that. So it's already got a safety margin built into it. It's not as sensitive for low-level faults. The restricted earth fault will see that. You don't get low-level external faults, you get low-level internal faults. So that's one that we do use at times is that restricted earth fault, a high impedance. We sometimes use a low impedance, which is not as sensitive, but we can do that within the bias differential relay. So we use the same CTs as that, so it's a bit more wiring into the relay. That's what the schemes look like. The one on the left-hand side is a 275 kV arrangement. You can see that the two windings, that the AutoStar has one high impedance scheme around it, and well, this is actually an REF, not a high impedance REF. So there's one around, and you can see that neutral is just one CT. So there's only, off the neutral there, we've only got one winding. On the right-hand side, you've got a HV REF scheme and an LV REF scheme. So they need to be in separate windings or separate elements in the same relay. A low impedance scheme, which is the one on the right-hand side, you use the same CTs as the high impedance, but that would be inside the bias differential relay that we've got. The thing which you've got to watch with when you're using those schemes with inside a protection relay is that different manufacturers will use different algorithms to do it. When we first changed from the old electromechanical relays, the new electronic style relays replicated what the old electromechanical did. So they even went to the extent that a spinning disc takes a bit of time to slow down. We'll put an algorithm to mimic that. Now, we look at it nowadays and go, why? You want to know the currents drop to zero, why not instantaneously, or 1 millisecond? Why wait 5 milliseconds? It's because the engineers at that time, this was new technology, this is what we've been used to for 30 years, this thing you can't do it that quickly, that's their mindset. So the manufacturers had to replicate what was done there to get the protection engineers who are conservative people to buy their new products. That no longer happens, and the old formulas that were applicable to the old electromechanical, they go, I can do it with this formula differently, I will. So you need to look at the manufacturer's manual to see how they're actually doing it. It has caught us in testing new relays at times. Well, what have they done there? You read their manual and I don't interpret it that way. Someone in America means something different to how we would interpret it. Backwards and forwards we find it. Haven't really had issues in the field, but that's why we have a group of standard engineers that I work with, principal engineers who look at new relays, set them up, work out how we're going to use them, work out how they work, go and test them before deploying them. So it takes a bit of time to get through that as well. We said earlier, it's an ampere turns balance. All right. So when load current is going through, the ampere turns on each side of the transformer should be zero. The balanced if everything's right, if you've got a perfect transformer. It's not as sensitive as high impedance, but provides good overall comprehensive protection. With the modern bias diff relays now, you can share the CT core with other things if you need to. High impedance you can't, because by virtue you get high voltages through it, so it'll damage other types of relays. So you can't share high impedance circuits. That's a disadvantage for them. And they're very stable for external faults, and they're very fast to operate. It's written down there as 30 milliseconds, but the ones we're getting now are in the low 20 milliseconds. And for the network, the faster you clear a fault, the better it is for stability issues. And we've got a time limit of 100 milliseconds as well on top of this. But we well and truly meet that. We're about 80 milliseconds. Your circuit breaker takes up a big amount of that. We've got 2-cycle breakers, they're 40 milliseconds. Our old circuit breakers are 60 milliseconds. So you've lost 20 milliseconds, 20% of the time, just by an old CT there. You still clear them in 100 milliseconds, but only just. This is a simple picture of how, if you had a 10-to-1 transformer, 100 amps on one side, 1,000 amps on the other side, 100-to-1 and 1,000-to-1 CT ratios, you get 1 amp secondary flowing through both CTs in the opposite direction. You get no current flowing through your relay down the bottom there. So that's the simple theory behind it. But we put a bias winding in there, a bias or restraint winding. And what that does is, as you get more current through the circuit, puts more of a bias or put more of a restraint on it. Because if you've got errors and they equal a few percent a lot of current, a few percent of a lot of current is a lot of current. So this just puts a lot of bias or restraint on it. That'll show up shortly when I've got some pictures of how it looks, but it does make sense then. So we introduce this bias or operate winding for undesirable unbalances, CT errors, VT errors, those sort of, well, not VT errors, CT errors and transformer mismatches that happen. The restraint quantity is given as this I1, absolute value of I1 plus I2 divided by 2, and the operate quantity is just those two subtracted. That's the typical old electromechanical standard way of doing things. That restraint quantity, the picture coming up, Siemens do it differently. So they don't have the divided by 2, I think, from memory. So you'll see that coming up in a slide. I'll point that out. It's quite simple when you're working out what you need to do and how to set these relays. You just use their equation, not this old equation. But many relays will still default to this. Others do it differently. That's why you've got to read their manual. There's a number of factors that you need to take into account when you're designing these. Is the current imbalance by the CT, but by the tap changer on your transformer, the transient response of your CTs. It's not only the normal current flowing through when you get an external or internal fault, but more so an external one. You're going to get a lot more current and you get a transient performance on your CTs. If they're mismatched, that causes an unbalance of current in your secondary. You don't want to trip for external faults, it's external. Internal, you do want to trip. So you do need to be over top of those. Phase shifting is also a concern. Dealing with zero sequence currents is another issue you've got. So a star transformer that's got the neutral earth is a zero sequence source. So to the HV, if it's, depending on which side it's on, the external CTs, one of them won't have that zero sequence current flowing in them. So you can, if you don't take that into account, you can trip because it's a zero sequence source. Your inrush current is another concern. So the mismatch between transformer turns and the online tap changer, the magnetising current in the CTs, and the CT ratios, actually we select those in the reverse ratio. It doesn't matter now. The old CT, the old electromechanical relays, you had to select ratios of CTs to try and keep that current balanced. You didn't have that perfect 10-to-1 transformer. You had a 10.5-to-1 transformer, so you didn't get CTs matched like that. For the zero sequence, we used to have to connect the deltas up in CT, so we ended up with CTs not with a 1 amp secondary, but with a 1 on square root amp secondary. So we used to have to take those sort of CTs. So it was very complicated with the old electromechanical. Now, the first two, you just got a percentage error, and we just put that percentage error in there, and that's how you just set it. The mismatch, yeah, and then the modern relays adjust for the magnitude current difference in the relays. You tell it what the CT, in simple terms, you can tell it what the CT ratio is, and it multiplies that by the current it's getting from the secondary, so it knows its primary current. So it can be any sort of ratio. If there's a phase shift across the transformers, we used to have to compensate for that in CT wiring, the same with the zero sequence. We don't need to do that now. They've got mathematics basically in there, a matrix arrangement that takes care of that. You tell it what matrix you want it to use, and it'll account for your phase shift and your zero sequence source. So the old ways that used to be done, if you had a YD1 transformer, your HVCTs had to be connected in delta, so star delta, the YD stands for, and the LVCTs had to be in a star, and so on down through there, through the different ones. So you had to have that consideration when connecting up your CTs, and that was always a source of human error. If they connected up wrongly, you would trip spuriously. They usually found that out when they turned the transformer back on. They get a trip. Go back, check their circuitry, got one back to front. Or we were told it was one type of transformer and it was actually a different one. So we got the settings wrong. That didn't happen very often, to be honest. But this is how they do it now. This is a cell 387. We use 487s now, but they still got the same matrix. So you got from 0 to 12 is what you can select from. The 12 gives you a 360 degrees, so you're making no difference at all at 12, but you're taking out the zero sequence. 1 is 30 degrees, 2 is 60 degrees, so YD 1, 2, 3, 4, so on like that till you get to the 12. What I've done here is the maths for one of them on one of the lines, and you can see how it works. So this is a YD11 transformer, so we select the 11 there. That's what we need to compensate for it. So the IAWNC stands for A-phase winding compensated. So that's the formula. You got that matrix there, you end up with a formula for your A-phase as being the A-phase current minus the C-phase current divided by √3. You work through the maths. Your A-phase is 1 angle 0. Your C-phase is 1 angle 24. You subtract them, you're going to come up with that value of 1.5 plus J 0.866. You divide that by √3, you come up with 0.866 plus 0.5. Put that back to polar, you get a 1 angle 30. So A phase going through the transformer, a YD11 transformer, is going to be shifted because the 11 is a minus 30 degrees. You need to shift it back up 30 degrees, so that compensates for the A phase current on the LV side. The one is, look, the ratio, you've got to have CT ratios in there as well. That's a separate sort of equation which gets done. This sorts out the zero sequence and the phase shifting. Another little compensation formula in there needs to work out the mismatch in CT ratios for the transformer. So that's basically how they're doing it. Tell me what you've got out there, I'll fix it up in maths and I can convert whatever you've got in mathematics to what's actually happening out in the real world. Tell me how your CTs are connected as well. So you don't have to worry about what you're doing, you just have to set it. Transformer inrush, that's another thing you need to be concerned about. It actually has a high level of second harmonics in it, so we put a second harmonic restraint in there to prevent tripping on inrush. Overfluxing is caused by overvoltages and under frequency. This has a lot of fifth harmonic. We put a fifth harmonic restraint in there. You've got to protect for overvoltage and under frequency, but that's a network thing. That's not a transformer fault thing. So the operators or some other protection has got to take care of that, not your transformer protection. So you can have up to about 5 CTs in these transformers. So what that would be is if you've got a breaker and a half on one side, breaker and a half on the other side, and a tertiary, and you've got all your CTs brought in individually, that's 5 CTs. So you can protect a transformer like that. Do you know what I mean when I say breaker and a half? One nod, couple of nods. All right, we haven't got a bit of paper. Our 275 kV buses have 2 buses only between them. We've got what we call a diameter which joins them together When you get very big plant that you need really reliable supply, like Boyne Island, an aluminium smelter, they use about 1,000 MVA continuously, you have 2 circuit breakers. So you have a bus fault, you don't lose any plant item. But at the transmission level network, if you have a bus fault and a CP fail, you only lose 1 plant item. At the transmission world, we put 2 of those things together. That saves on costs. So where we would have 2 plant items, instead of having 4 circuit breakers, we have 3. And 2 plant items sharing it. I didn't notice that. That's why we call it a breaker and a half arrangement. 3 circuit breakers looking after 2 plant items. So the one in the middle is called the coupler breaker. That's between the same. That's a common plant item. So if we get a fault on a plant item, transformer will trip 2 circuit breakers. The adjacent plant item in that diameter, like the feeder, will only be connected by 1 breaker to the single bus. It can still get out because you've got multiple diameters. Still get out. The current flow can still get out because it goes onto bus 1. Then it goes on to bus 2 and on bus 1, spreading around where all the current flows are going out of the sub. The only problem is with that coupler closed, if you now get a bus fault on bus 1, you lose that plant item where you wouldn't. But transformer faults are not very common, bus faults are even less common. That's a pretty bad day for the cost saving that we have. That's the risk how all transmission utilities do it. Must say I'm not sure what they do at 500 kV down south, whether they have breaker and a half or double breaker arrangement. But like I said, Boyne Island is the only double breaker arrangement in Queensland, and they built it back in the early 80s for what they wanted, a reliability of supply. You lose supply to your aluminium smelter for a number of hours, it solidifies, and there's a $300 million event that they have. Back up. Yep, that's I think where we were, somewhere, yeah, 5 CT inputs. Yep. So that's, sorry.
Give me 1 second, I just want to...
That's what I say when we've got a breaker and a half arrangement. I've got a board here or something to write on, but anyway. But we don't use that at 132 kV. Everything's a single breaker in that arrangement. And we're not moving away, but the renewable connections want to do things cheaply, so we start to create what's called a mesh arrangement, which will mean for 2 plant items, we've got a feeder which gets turned in and out. There's 4 circuit breakers. We still need to trip 2 circuit breakers every time, but it's less reliable, but it's cheaper. That's what they want. That's what we do. Yeah, and you can do multiple functions in these relays. So in all of these relays, we do our circuit breaker fail. So we go and trip the circuit breaker, and we start CP fail internal in the relay as well. So this is, you've got your data acquisition. This is how it looks like. You've got some fundamental frequency filters, 2nd and 5th harmonic, what your tap settings are, scaling for that, and then you've got that compensation that we just went through, and you come out with a compensated current that they use to compare their bias dip. It's basically how the internals work. This is what I was saying. You see the diff down the bottom, in the middle there, is just I1 plus I2, and the stabilised bit or bias diff or restraint, so it gets used different terminologies, but this is a Siemens one, they call it stabilised, is just I1 plus I2, whereas before that was divided by 2. But what you'll see is you get more current down the bottom, so that's an external fault will pull a lot of current through the transformer, so that stabilised current will get bigger. And what happens is that line going up at an angle that's getting bigger. So you need more differential current to trip as your stabilise, they call it, but as your bias current gets higher, you need more differential current. So if your errors are increasing, it's compensating for that. It means that it really does need to be a lot. So it helps with your errors and your CTs happening, that you don't get a external fault causing an unbalance in your bias diff to trip. There's a picture coming up which will show what internal faults look like, but here you've got that 1221, that's your pickup. So we put a safety margin on there of 20 or 30%. We generally follow what the manufacturer suggests. You've got one slope down the bottom line there through the origin. You've got a second steeper slope starting at that base point 2 at a second one. Anything above that line we trip, anything below that line we don't trip. And the bottom little bit there for IDIF is like, that's where you may have tap change. If you have a look and you've got a big variation in your voltage on one side because of a tap changer, you'll have different currents flowing, but it's still stable. So for a 100 MVA transformer that's got 100 MVA in it, the current flowing when you're on bottom tap to top tap is quite a big difference. It's just normal, balanced operation. You need to account for that. But that very top one is one where they don't do any of that filtering. So if you get a very high fault current, differential current, it just says anything above this must definitely be a fault internal. I'm not going to do any filtering, compensation or anything. I'm going to trip. So that's how you can get an extra 5 or 10 milliseconds in speed by not going through the filtering. The problem with that is if you do it at too lower level, you can trip for things that you haven't filtered on, which may destabilise your bias. So setting that, you have to be careful and confident, and we do set it like that. So the blue line represents a fault. So remember before it was I1 plus I2 and the effective quantities? If it's an internal fault, you've got current coming in both directions. So you'll tend to be along that 45-degree angle. Not exactly, but along there. That's where it trips. The blue line represents an external fault, so it goes from A to B. You get a lot of this bias, differential, stabilised, restraint, whatever you want to call it, and it's blocking the relay from operating. So that line along to B is how you can see you start to get that. It'd actually be better if that was sloped up a little bit, because your errors start to increase and it will lift up and probably be above the pickup line if you at 1 amp restraint, but it's in a blocking region. If the CT saturates, what happens, it would move from B to C, which is in the tripping area, but the relay says that's typical of a CT saturation, I'm not going to trip. The fault gets cleared externally and it comes back to A. So that's how modern relays can cater for a CT saturation, but they need a certain amount of current, they need a certain amount of good current, pre-saturated current, to be able to tell that it's a saturated CT, and so not trip for it. So even though it goes into the green region and trip, it won't trip. Now that's what they say, that's what they don't guarantee, that's what they say and how their things operate. There can be a safety margin in there. My preference is to set your CT so it won't saturate. Then you don't have a problem with CT saturation. But you need good quality CTs to do that. So that's why we order the PX class and order good ones. We actually allow our CTs to saturate at maximum fault level, so a fault level of about 40 kA and an XIR of 20. So they have to be, we only got a few sites like that, close to the synchronous generators. They have a high XIR and a high fault level. Our CTs will saturate in 40 milliseconds then. You send out your trip signal in about 20 or 25 milliseconds. If you've got that much fault current, you're going to be above that pickup that I mentioned, that top one, and you'll be sending your trip signal out in 20 milliseconds. So the decision is already made for you. If it saturates, if it happens to be external, you actually don't get all of that current flowing through because it's got multiple ways it's going. But if it did saturate, we've got 40 milliseconds is enough time for a relay to be a modern relay that we buy to be able to determine that it's a saturated CT. It's actually a lot more. Probably what they're specifying to you or tell you you need would saturate in 5 or 10 milliseconds. So we're still very conservative. That's just another drawing of how that can be shown. The 87P stands for a differential operation. So it's the same thing, 2 slopes, a pickup of 0.3, a slope of 25%, a slope of 60. That looks like it's come out of a relay manufacturer manual. That's what we would use. We do our calculations, compare it to this. If we say we need more, we'll make it more. If we say we don't need that much, we'll use their settings. They've got feedback from wherever they're selling these relays, and they say our relay is stable and works correctly with these settings. So that's why we use them as a default, but we check by doing calculations ourselves. Do we have something unusual in our network where we need to set that higher? So for setting one of these bias differentials, we go generally 20% above the line, representing the worst mismatch of the CT ratios and the tapping. So we look at top tap, bottom tap, and see what the mismatch is with the CTs, and then put a 20% margin on that. You'll see this 20% margin put in just about everywhere with protection. It's just a safety margin that gets used, which is, again, decades old. It works. Not too conservative, not overly aggressive that you trip incorrectly. One thing you don't want to do is trip incorrectly. So here's an example. This is an 80 MVA transformer with a delta tertiary, which would be 11 kV, protected by a bias diff, and it's on the windings, the tappings range from -15 to +15, so we go from 112.2 to 138.6 kV. The CT ratios, which are chosen, are 600 and 1200 to 1. 80 MVA at 132 kV represents about 380 or 350 amps. So that's why the 600 is there. You also need to check, so that's based on load of the transformer. The other thing to check when you're checking a CT ratio is its transient performance, and that's, you want to look that it doesn't trip on a need point voltage. And watch the mismatch at the end. So that's our transformer. You then select a tap to look at. We've got the voltages there, we've already been through those. Select a convenient to current to work with, so we can work out a ratio. So we just assume 600 amps at 132 kV. So on the 132 kV side, 600 amps divided by 600 would be a 1 amp. On the LV side, if it's got 112 volts, that you can see that's the biggest one away from 132 kV, so we just look at the 112, you'll end up with 0.85 of an amp. So if you do their restraint, you get 0.925 amps secondary. If you use their diff, is 1 amp minus 0.85, so you got 0.15. So 0.15 amps difference between the HV and LV secondary current is just a tap changer. So you don't want to trip on that. So you get your diff divided by your restraint and you end up with 16.2 amps, 16.2%. So that's the slope that we want, is 16.2. We put a margin of 20% on that, we end up with 19.4. this manufacturer represents a slope of 20%, so we use 20%, and they say for the second slope, use 80%. So that's how we get above that. The other thing there is that pickup at the bottom is not mentioned here. That'd be 25%. You've set your relay. You can see that bias down the bottom, or restraint, stabilised, all of those words mean the same, is divided by 2. That's where you've got to look at the relay manufacturer, what they're doing in their relay, how they're working that out. Yeah. So if we pull all of this together then, so the 1 MVA transformer, we only use fuses. At 10 MVA, you can use an overcurrent and earth fault. 20 MVA, a bias diff, and often they're then also done with an overcurrent and earth fault backup. Greater than 20 MVA, you can use duplicate bias diff or a bias diff and high impedance. And all of these have Buchholz, a PRD, and temperature as well, both winding and oil if possible, where you can do it. I'd also add in there that under the rules, it's voltage dependent, so not size of transformer dependent. So if we've got a little transformer, a little mine site that wants to connect to our network that's only got 5 MVA, you can't put a fuse on there that takes a second, or fuse might take half a second to clear, or an overcurrent that needs to grade over top of their protection, which takes a second to clear. We have to clear it in code time. That's automatic access. Or we have to do detailed studies and keep doing studies to say, if we take this long to trip, what's the impact on the network? And we clear the feeder faults in 100 milliseconds. It's the HV terminals of the transformer, we tell them, need to be cleared in that time as well. So it isn't just rating of the transformer, it's also voltage level under the rules that it connects to. But that's not common. We get small, not common, no, it's not common, but we've got about 3 or 4 of these really little transformers that have connected to our network, because we've got electricity in the townships 100 kilometres away. So it's too far to run a 1133 kV feeder. You just have big voltage drops at the end, and very costly to do that. Now, looking at an earthing transformer, I'm not sure if you know what an earthing transformer is. So when you get a star-delta connected transformer, the delta doesn't give you any earth fault current. It's actually in isolation in a zero sequence network. So to get earth fault current, you need an earthing transformer. They'll also keep the voltages down when you've got earth faults. So you don't get floating voltages, you don't get over voltages with it's called a voltage rise on healthy phases. But the earthing transformer will only have a zero sequence current. So it also gives an earth reference, and actually it gets used a lot in far north Queensland. We've got 132 to 22 kV. They've got a 22 kV network. We've got these 132 to 22 kV step down transformers, which are star delta, and then we have an earthing transformer. So for the 22 kV network, that's the earth reference for them, which will give them earth fault current so that they can set their protection. So it has that advantage, as it keeps the over voltage down, and then it makes protection a lot easier. There's 2 types of things we need to consider when protecting earthing transformers. There's the internal faults, and the uncleared external faults. So that's the arrangement that you've got. A star delta transformer on the left-hand side. You see the earthing transformer. It's also called a zigzag transformer. That's also another common name for these type of transformers. So if you've got your load on the right-hand side, so this would be the typical 132, 22 kV transformers that we've got. They range in size from about 20 to 50 MVA. if you've got an external fault there, earth fault, outside the transformer zone, you get earth fault current flowing in your earthing transformer up the neutral there, through each of those windings. You get 2 units going back, so that's all zero sequence current, and it's I0 in each phase. So you get 2 lots flowing back into the transformer, coming out on the faulted phase, plus the single coming up from the that phase on the earthing transformer, and you get 3 lots of I0 current flowing out. So your earth fault current, total earth fault current is equal to 3 times I0. It's where your 3 lots of I0 come from. The CT in the neutral leg is just sitting there, and that's doing a definite time and an IDMT earth fault. But the CT is sitting in the phase currents, if we'll call it that. They're connected in delta. The reason for that is to trap the zero sequence current. So you see for that earth fault current external there, they've got no current flowing through the relay. So it doesn't matter how big that external fault is. So what that gives us the advantage, we can set that overcurrent element really sensitive, and it only sees faults inside the earthing transformer. So we said earlier that overcurrents can't be set sensitive. Well, this one can be because of the way we connected it up and because there's only zero sequence current flowing for external faults. You won't get phase current. You won't get any positive or negative sequence current out of your earthing transformer. You only purely get the zero sequence current. So that's what that's really just saying there. We set it sensitive, but it just must be set above the inrush and the magnetising current. And we usually use an IDMT curve for that. You need to consider the short time rating of the transformer and make sure that the earth faults are below that. And we use a combination of IDMT and definite time for the external faults. So the IDMT earth fault protects against uncleared external earth faults. Set below the short time rating of the earthing transformer, it needs to grade over top of downstream protection, and it provides a backup to the LV network as well. So just a level of redundancy. It's one thing in the network that we've found over years of experience that it's good having a degree of backup even when you're not required to have it. That helps a lot. I don't know if you remember, it was May last year when there was that Callide C event and we had blackouts throughout Queensland. That was all protection that operated and cleared that was not designed to do that. It provided a level degree of backup, but was never designed to clear that type of fault. But it did. Still had blackouts, but if we hadn't cleared it like that, actually basically what happened was all the remote feeders from Calval, which is where Callide C connects to about 1 kilometre away, they tripped. The fault evolved into damaging their generator transformer, evolved onto the HV side, and they'd lost all communications to the outside world, so they couldn't tell us to trip. We had old relays on that feeder. It's meant to be replaced, but we're waiting for an outage with theirs. So we didn't know that they didn't have communications to us. But what happened, all of those remote feeders tripped, cleared the fault. If that fault hadn't been cleared, there would have been a lot more plant tripping across Queensland and the eastern seaboard that happened. So having this low voltage backup, it's not in your mandate, but it does provide a degree of backup that is easy to do, secure, and gives you a little bit extra for nothing. It's basically how I say we do it. It's not intended to work, but it can. And it's not the only time that sort of thing has happened over the years, seeing that happen. The definite time is more around, we know the continuous rating of the transformer, we set below that, and we operate quite slow. So it's not in protection operation time. We've got the example to say that it's just if there's a low voltage fault or an unbalance in their network that's hanging on for a very long time, we trip the transformer. They're always inside the bias differential range, so we're not really worried about a high-speed operation for a low-voltage terminal fault. The bias diff will detect that and operate. So we're not after high-speed operation out of this. So it's the grading with the LV network. So I forget which substation this is, but it's a 22 kV. The earth fault is 380/20. The short time rating of the earthing transformer is 4,600. The continuous rating is 120 amps. The LV network that we need to grade over has an IDMT standard inverse curve with a pickup of 80 amps and a time multiplier setting of 0.2. So to keep things simple, we use the same pickup that they do have, 80 amps, and then we grade 400 milliseconds above that. This is a little internal program that we've got. You can use those formulas for the standard inverse in Excel or any sort of program in MathCAD, any sort of application like that to do this. Someone internally wrote this in the 90s, so a very long time ago, before Excel was even around. This is actually Ellarish, a substation in far north Queensland. So you can see what's on the left-hand side, the line straight up, is the continuous rating. The red line is the ergon IDMT curve, and the green line is our curve. So you see at the maximum fault level of 3,820, although it's hard to pick up on that log scale, we have a 400 millisecond gap. And it's hard to read, but you can see a time multiplier setting in the green of 0.43. So if you just went through the maths with that current, you'd find that that's the current difference. You'll see that the green curve sits above the red curve all the way through there. That's the advantage of picking the same pickup as they did and just changing your time multiplier, just shifts the whole curve up. It's going to be a bit slower, but it grades over top of all the protection downstream. It protects the local supply transformer because it's rated for 4,600 amps for 3 seconds. So you're going to clear a fault at that level in about 0.8 of a second. So we're well below the short time rating of the earthing transformer. So our transformer's happy. Their protection should operate. If it doesn't, we'll trip out. That's the basis behind it. So we know the continuous rating is 120 amp. We just set a definite time. We take 80% of that 120, which is 96 amps, and we push the time out for as long as we can, which is usually around 600 seconds, and we'll say we'll trip after 600 seconds. So if there's a current flowing in the earthing transformer that's 125 amps, we'll clear it in 5 seconds and we won't damage, 5 minutes, and we won't damage our transformer. Actually, the earth fault IDMT curve will pick up and trip before that. But the combination of both of those keeps the transformer protected. Where are we? Right, any questions on those? So that's what I've got for the end of the transformer protection, if there's any questions. Right, one thing that's unique to transmission protection is the speed of operation, which I said earlier, which for our feeders is 100 and 120 milliseconds, or 120, actually we've got 220 at 330 kV. You can't discriminate at 220 very well, but you can a little bit. But for our 275, 330 kV network, you need protection signalling to be able to clear correctly and discriminate. So that's your basic distance scheme. Have you done distance protection yet? Yep, all right. So your zone 1 trips instantaneously, it's forward looking. When we set them, that LEC's aligned end closed. That's all you need to worry about. If your remote end breaker is open, circuit breaker is opened, you're not going to trip spuriously. The fault can't be beyond, you can't see a fault beyond that because you're not going to send current through. So you're not worried about a aligned end open scenario, which is what we call an LEO. So you can trip instantaneously because the fault can't be beyond the feeder. So we only look at lined end closed scenarios for our zone 1. Oh, I've got what those definitions are there. Zone 2 is forward looking. We ideally want to cover all of our lined end closed cases, including arc if possible, but sometimes including an arc impedance can get you very big reaches that are not realistic, and you can allow sequential tripping. If you've got a lot of arc resistance, your fault current's a bit lower as well. But the zone 2 must cover all lined end open scenarios. Because if your breaker's open at the other end, nothing else is designed to see the fault on the feeder. The distance relay at my end here is designed, has to see the faults on all of it. None of the other protection in the network is designed to see faults on this feeder. So I must cover all lined end open cases. When you're also doing zone 2, you have to consider, do I overreach onto other protection? And what are the consequences of that? So in our network where we've got a lot of big feeders, not often we have that zone 2 overreaching problem. It's only when we've got short feeders that remote feeders may see onto those remote zone 2s. If they're too short, we've got duplicate current div. So to get a spurious trip of a zone 2 overreach on our network, we've actually got to have failure of 2 lots of communications or a relay and a communications failed. If we actually had 2 relays fail, they've got to take the planned item out of service. So it's not such a big issue for us, but it is a concern that you may have in some areas. And to me, it's also looking at the consequences. So when I set a short feeder, I'm happy to set the zone 2 time delay a bit quicker so the remote zone 2s don't go before or at the same time as I do. And it was those remote zone 2s that cleared the fault on the generator transformer. The problem with that, all the feeders into that substation tripped, which was good because nothing else saw the fault and cleared it, so we did clear it. But if you had a distance relay on that feeder and the zone 2 set to 100, 200 milliseconds, we would have cleared just that feeder a little bit quicker and less impact on the network. That's the consideration when you're doing these settings. You just need to think. So for the transmission network to achieve those code times and discrimination, as I said, you need signalling to get 120 milliseconds. If your feeder on a sub going out is to clear in 100 milliseconds, you've got to clear in 120, but you've got to say it's on the feed, my feeder, and not 15, 20 or 30 metres over onto the next feeder, and our feeder is 100 kilometres long. 30 metres in that is just errors. That's 0.03%. You can't distinguish between a fault on the end of your feeder and the start of another feeder. And you've only got 20 milliseconds less to trip faster. You've only allowed 20 more milliseconds in time in the code. You can't discriminate because 40 milliseconds of that time has to be your circuit breaker. So you've already sent out a trip signal when his breaker's opened. Our 2 schemes are permissive and blocking. They operate on different philosophies. So zone 1 is always a trip the circuit breaker. The zone 2 is I've got a zone 2 and I receive a permissive intertrip from you, I trip. A zone 2 plus our zone 2 time delay, we always trip. So protection signalling doesn't stop the relay from going in a slow zone 2. It basically just speeds up that slow zone 2 for a fault on there. So we term it, if it's just a zone 2 operation, the terminology we use is slow zone 2. You see it's not written there, but that bottom one being a zone 2 and the zone 2 time delay we term slow zone 2. The middle one, where you get a zone 2 and a protection signal to get you to go quicker, we call a fast zone 2. That's just the terminology that we use. So both of them are a zone 2 operation, but one's just faster than the other. So there's two types of permissive, an underreach and an overreach. We tend to use overreach. So what the difference is, a permissive underreach gets sent on zone 1, so it doesn't get sent for all faults on the feeder. For that to work, you must have overlapping zone 1s from both ends. If you don't, the zone 2 seen from both ends, a fault in the middle of the feeder will go in slow zone 2. If you've got a permissive overreach, you see all faults on the feeder, but you also see faults beyond the feeder, so you send the signal there. But if your remote end relay doesn't see it in zone 2, it doesn't do anything. So that doesn't really matter. One simple way to think of permissive overreach, it's like, or permissive signalling is, there's a fault down, you're the relay at the remote end of the feeder, I'm the relay at this end of the feeder. I tell you the fault's in front of me, you tell me the fault's in front of you. It's got to be between us. It can't be anything else. So that's the way it works. You tell me that and it's right in front of me, but my zone 1 is already tripped. I say, oh, thank you, I know that, I've already tripped. And it's in your zone 2, you go, oh, you told me it's in front of you as 2, I'm going to go. It's not in my zone 1. If it's in each other relays, both zone 1, this signalling does nothing, because we've tripped instantaneously on zone 1 from both ends. And the scheme should be the same at both ends. So if you've got a permissive underreach at one end, it should be underreach at the other, and overreach at the other. The other advantage of the permissive overreach is that it sees all the arc faults as well. So it's got better resistive coverage. So what it actually looks like on the curve is that it changes that grey zone 2 into that green fast zone 2. So for faults on the feeder, we'll go quickly in code time. The logic of it looks like that, a permissive underreach. So zone 1 goes through and trips. Zone 2 goes through at zone 2 time delay, typically 400 milliseconds, and trips. And zone 2 and a receipt for the signal from the remote end just goes through and trips. So the difference between zone 1 and zone 2 time tripping is just the protection signalling time delay, which is usually in the order of 20 milliseconds, 15 milliseconds. So it's quite quick. And the previous one here, you saw for permissive underreach, the signal gets sent on that zone 1. Permissive overreach, the signal gets sent on that zone 2. The PIS stands for permissive intertrip send. The PIR stands for permissive intertrip receive. So a fault in the middle of the feeder, both relays see it in zone 1, they both trip instantaneously, and they both send signals to each other for permissive reach and overreach. So a zone 2 always encompasses the zone 1 and is just bigger. It's not an area on its own. So if you turned off zone 1, zone 2 would cover the whole feeder. So that's why for permissive overreaches, which just get sent on zone 2, the faults in zone 1, it will send a zone 2 fault. It will send a permissive signal as well. The fault's close to relay A. Relay A goes instantaneously and sends a signal to relay B. Relay B waits, it can see it in zone 2, and when it gets that signal, it goes and trips the relay. No signal is sent from relay B for a permissive underreach. For permissive overreach, it sends a signal. A blocking works the exact opposite, basically. We don't have a lot of this in our network now, but it was quite common in the past when we used to use PLC communication, power line carrier. So you were sending communication signals over the physical phase conductor was what was happening, just at a different frequency, but over the phase conductor. If that phase conductor is having a fault at the same time, you've got to send the signal through the fault. Now you can do that, that's not impossible, just increases your probability of not getting through a little bit. So we use a blocking scheme which works in the opposite way. So what it works is we have our zone 2 set to go quickly. If we don't get a signal from the other end, we go quickly. If we get a blocking signal, we do. So I see it in zone 2. You see the fault behind you, so you do a setting for reverse zone 3. You set the signal behind you. Has that got it up there? Yep. You tell me the fault's behind you, I don't go quickly. You tell me nothing, and I go. So the fault's in between us on a phase conductor that we're sending PLC. We don't actually send a signal at that time for a feeder fault. We only send signals when the faults are behind us and not on our feeder. So we reduce the risk that the signal won't get through the faulted phase. That's just all. Now, we did use permissive signalling on PLC, and I don't know the statistics of how many times they didn't get through or what, but it wasn't that bad. It's not that it's bad, it's just that wanting to mitigate your risk, change to a blocking scheme, you mitigate your risk at no real cost. Well, it's no cost, you just have to design a little bit of extra work. So I've explained all of that there. The way we set our zone 3 is you use the remote zone 2, so you need to be able to see further back behind you than what I can see beyond you. That's the logic behind it. So my setting, my remote zone 2 setting, we multiply by 120% for a safety margin. We take off the feeder impedance because that's between us, and then we multiply the lot of that, so that multiplying me by 120% is the absolute furthest I'm going to see. You then go 20% over top of that, less the feeder impedance, that's your setting. So that's the basis of it. So you don't need to do reverse zone 3 studies, you just need to get the setting for the fault that you're on. You just need to get the setting of your remote end feeder. So you have to set these both ends together when you're doing this. Yeah, that's what I've said. We go fast if you don't get the signal. It was good with power line carrier. Yeah. So for that fault which was in a zone 2 before, if we've got a blocking scheme, you see that now there's these reverse zone 3s in yellow from each end, and they see further beyond, they extend beyond their remote zone 2s. So we're covering those there. So for that fault where we had before, zone A goes instantaneously, zone B sees it in its fast zone 2 time, so it waits about 50 milliseconds to receive that signal from the remote end. If it doesn't get it, it trips. So we'll leave that at that step. When the fault's not on the feeder, the relay A doesn't operate at all. It's not a fault on the feeder, but it sees it behind it. So I see the relay fault behind me. I send you a signal, tell you block, don't go, because the fault's not between us, it's behind me. But what you do is wait, you slow zone 2. So if the fault's still sitting there, you're going to trip. So nothing stops the slow zone 2 operating. So that's the way the logic looks like this. If you see it in a reverse zone 3, you send a signal to the other end. Because the other end is waiting to go quickly and we lose one signal, you're going to could trip incorrectly. We send 2 signals. So the BS stands for a block send, and we send an A and a B, different paths, so different ways to get there, so it's secure, reduce the common mode failure. So down the bottom you see a receive A or B, so it's not one of those, not both of those comms fail. So if both of those communication paths fail, we put a permanent block on there, so it can't go fast, can only go slow. So you see the zone 2, with the zone 2 time delay going straight through on the right there, nothing stops after that time delay a trip. So that's a settable setting that in all distance protection you do. You do a zone 1, a zone 2 with a time delay, and your zone 2 will always operate after that time delay. All of this protection signaling, as I said, is getting things going quicker. So we've got that block time delay on zone 2 that you wait. So you see it in zone 2, we wait, you go through that AND gate. If we don't receive a block A or block B, and we don't have comms failure on both of them, we go through after that short delay, blocking delay, which allows the signal to be received, and then you trip quickly. They're just a whole lot of abbreviations. Another type of feature, whoops, just go OK. I don't know what I need to do there. Keep going here. There's a weak in feed. They tend to be in radial ends of the network, a weak in feed. So if there's a big generator behind me and I'm happy, and this is in the Serac, we've got that, you can be weak. So for faults in front of you, you don't have any current because we've got no generation down there. There's just all the gas fields. So there's no generation, just load. There's zero sequence sources on some of the transformers, but for phase current, there's not. So you're weak. But for faults behind you, you're strong because you've got the same source I've got, just a bit of a distance between us. So you can see faults behind you, you can't see faults in front of you. So the way we set a weak, it's just a setting in the relay, you tell it it's weak in feed, it says, all right, that's just a feature. If you're a weak in feed and there's a fault on the feeder between us, basically the way it works is I send a signal to you to tell you I can see a fault in front of us. If it's behind you, you say, yeah, I can see it too, but it's behind me, and you do nothing. If it's a zone 1, I'm already going to trip. If it's a zone 2, I do nothing as well. But if you can't see it behind you, you then go and look at your voltage. So you may be weak in feed, but your volts will still be, won't be healthy. So you'll see you haven't got healthy volts. You can't see a fault behind you. I've told you you're weak in feed, that you're blind to faults in front of you. I can see a fault in front of me. Then we just make the logical conclusion that the fault must be on the feeder. So you echo that signal back to me. So if it was in my zone 2, I'll go quickly. If it was in my zone 1, I've already tripped. So you trip and echo a signal back to me. So we've got to have those 4 things. Set the weak in feed. So I tell you, you can't see faults in front of you very well. That you don't see it behind you. So you don't see it so you can see faults behind you, but you don't see it there. You see that there's a fault on the network somewhere, the voltage is dipped, so there's not healthy faults. And I've told you the fault's in front of me. That's when you combine all of those together, and then you make a jump, a conclusion. But you really don't see the fault, but it is in front of you, so you trip and echo back to me. So that's how a weak in feed works. There can be parts of the network which are not weak in feed, but we take a feeder out of service or the generator's offline for maintenance or something, and it becomes a weak in feed. If that's the case, we just turn on the weak in feed. If you see the fault in front of you, you still send a signal to me. So if you do see it in zone 2, you still send a signal to me. They're always used with permissive overreaching schemes. So if you see it in front of you, you send a signal to me and tell me to trip. If you see it in your zone 2 and I send you a signal, you trip. It's just if all of those come and you receive a signal from me and you can't see it in front of you, you then got to make some more decisions along the way. Is what's happening. That's basically what all of those words say there. That's come to the end of that. Well, we've got 5 or 6 minutes left if you've got some questions there or anything. What's happening in the network? Well, lots, to be honest. It's getting very busy. What year are you using?
most of them are final year.
Final year.
Master students.
That's good. So PowerLink, I know, has opened up. Actually, I think they put on their new graduate engineers.
So they've all
Yeah.
I've done make it. I've done this.
Yeah, that's what I was going to say. We've got an article out about it. Yeah, they're putting on some extras this year. I know they were. But there's a lot of work coming in our industry, so you're coming out at a good time. A lot of renewables connecting. A couple of years ago, most of the renewables were solar farms. Wind is now starting to come on, and the next big one, which is starting to come in a wave, is batteries. So we need those battery storage or a storage system. So the government's talked about a pumped hydro scheme, but that's all closed doors. PowerLink's working on it, that group's over in there, and it's all confidential, but they're looking at how can we store the electricity that we've got. One thing I went to a talk to many years ago, and it was one of the senior managers in Transgrid explained this. He used to work at PowerLink actually, is that in the past we had these big Cygnus generators. We had a load flow that went like that during the day, so we'd ramp up the generators and down to match the load. Now we've got this variable generators which come in and out, solar farms, the cloud comes over, the wind stops blowing or something like that. So we've got generation which is doing this. We need to get our load to do this so that they can go in sync together. That's one way to do it. You've got to fill in some troughs and valleys which are batteries and storage systems. But one thing that's coming online where we may be able to move the load up and down a bit more is hydrogen. So if you turn them off for a period or turn them on, it's not like an aluminium smelter. It's not like a train. It's not like they do pulse aircons now, but it's not like a lift in a building where, we turn it off for 5 minutes to drop the load a bit. It's not load sensitive or time sensitive as like that. So there are a couple of interesting things that we're doing, and as part of that, we've got a new innovative technology that we're looking at, which we coined the word WAMPAC, Wide Area Monitoring, Protection and Control. So we monitor the whole wide network and can trip in different areas. QNI has a problem. We need to trip that generator in far north Queensland. Central Queensland to southern Queensland has a problem. We need to trip the same generator. So the logic is, why not just have one central bit that looks at all of these and then takes the similar actions across the state? In the variable generation, you need to know what's generating at the time. So we need all of that information coming back into a central point. So we're working on things like that, which is, innovative. Management supporting it, and you've got money to do things. That's a change. To be honest, it's good.
I have one question.
Yeah.
Donald, like in the distribution system, this reverse power flow is a key issue. But with the batteries coming up and connecting to the transmission network, do you think that there will be the power flow direction changes with that network as well? Because you have
at night, yes. So at low times when all of those PV come off, yes. The other thing is there going to be more batteries coming in the domestic network? Not sure about that. That's one thing which could change that equation that would happen. But definitely, yes, the current would go back then. But I don't think the flow back up in the daytime is going to stop. Battery, at that time, the price of electricity is zero. Sometimes it's gone negative. The battery gets paid to charge up. That's when they're going to charge up. And they spend most of their time doing nothing, batteries. If you have a look at them, they charge up, sit there flat for a long time and then discharge a little bit. So they're in the FCAS market a lot, so frequency control. So they sit there ready to guarantee that they'll control the frequency. So they're not charging or discharging, but they're actually probably at close to full capacity to discharge when the price is really low, which is good for our network, because our problem is, especially in spring, that you get peak in the morning, a dip in the day, and a peak in the evening, and then back in the night. So they're calling it a duck curve. Before you had a bell-shaped curve, now it's a duck curve, because in the middle of the day, spring and autumn, a lovely day like this, 26 degrees. All of the PV in the domestic network is pushing out power. People at work, not at home, using it. Although it's school holidays now. Plenty of power, not a lot of demand. No one's got an aircon